that the product, okay, product, Cartesian product is also known as, okay, seems pretty trivial, but it's not, because we are not putting any restriction on I actually. Okay, so if this I is finite and very countable, then everything is easy, or you can prove it easily. But there are gaps actually, not really gaps, but some people say that okay, we are satisfied with this proof. But some say that we still are not convinced that whether this proof is okay or not. I had once a talk in Warwick actually. There was a Baba who gave a very harsh critique of axiom of choice. There's something wrong with this result, and troublemaking is that this sits at the foundations of set theory. So if this is shaken, set theory is shaken. And if the set theory is shaken, just think about it, what is going to happen in mathematics. Because every single damn thing is depending on set theory. So give me a subject of mathematics which you haven't heard and learned, and it doesn't depend on set theory. It's a pretty foundational result. Okay? But the issue is that some people talk, let's not talk about this, let's talk about the other things, let's not talk about this actually. So it's a worth exploring thing when you go to the axiom of choice. There are positive things, but there are pretty negative things. Okay, so it's like the way we ask. So it's like for some of the question when we say that okay, let's not think about it actually. But if you think about it, so many fundamental things of yours will be shaking actually. Okay, you have similar things in mathematics. So let's not too much emphasize on this actually. So there is another thing which is equivalent to this axiom. So in other words, if you treat this as true, okay, then there is something that is called Karpowski's lemma. It's called Karpowski's lemma. Zorn's lemma? Have you heard of Zorn's lemma? No? Did you heard it in your oral algebra course? That's good. Fundamental. Okay. So the Zorn's lemma is not saying something unusual actually. You're going to see, if I write the statement of it, you're going to say that okay, we have heard something like similar somewhere. So what is the Zorn's lemma is telling us that imagine there is a partially ordered set, okay, with a partial order. Okay, so it's a poset. It's like a partially ordered set. Remember partial order? Have you done anything about lattices in your group theory course? Lattice? No? Okay. It's okay. Partial order. So do we remember order?
Yes.
Do you remember order? So you're going to say that this order is partial order. Okay? If following conditions are satisfied. Number one, that it must be symmetric. No, not symmetric, but what do you call it? Reflexive. Okay, so yes, it must be anti-symmetric. What do you mean by anti-symmetry? That imagine that some f is, less than or equal to g with respect to this order, and g is less than or equal to f, then f and g are indistinguishable. Okay? They can't be different things. And the third is obviously transitive. If all three conditions are satisfied, you call that you have defined a partial order on the set P. You have O set out. Alright? Now, if you have a coset, then the Zorn's lemma is telling us the statement. If this, can you see this?
Yes.
Anyone?
Anyone?
Let's put it here. So this Zorn's lemma tells us that if you have a coset, in other words, you have an order on a set which satisfies all three properties, and if every chain, okay, and by chain I mean a totally ordered subset. What's a total order? So by total order means that you have a kind of a trichotomy law in it. In other words, you can compare any two elements. Okay? So if I have a chain in P, that is, okay, if I write it precisely, that is that imagine you have something like this. You have something like this, okay? It's like a chain with respect to this order. So if every chain in P is bounded by an element of P, okay? Because every chain has an upper bound. Bounded above precisely by element of P, then P has a maximal element. Okay. And P has a maximal element. So have you seen something like similar somewhere? Did analysis, something like that.
Least upper bound, least upper bound.
It's really analog to that. Actually, it's not really okay, but it's analog to that. Okay. Because we know that this less than or equal to thing between numbers is a partial order. Okay, you can have change with upper bound, then the collection must have a maximal element. Is it making sense? But just think about it. If the least upper bound property in the real analysis becomes controversial, what's going to happen? So everything that is dependent on this property, gone. So I'm not saying it's controversial, okay? It's a bit, it is actually, let's be fair. but and it all comes because that the notion of infinity, we still don't understand the notion of infinity in a good and precise manner. Okay? And in the words of M.J. Wilberger, this Australian guy, that maybe it's time to give up infinity. But it would not be, that much easy, because that would be a was flood in the whole world of mathematics. everything will be in trouble. Anyway, so the topic of axiom of choice is pretty interesting. Must explore it. See what's wrong with it, what's good with it. What is the criticism of it, and how it sits at the foundations of set theory, and hence it sits at the foundations of everything actually. Are you getting the point? And what we are going to prove, today is something which is called the Hanhn theorem, which is we are going to prove through this Zorn's lemma, which is equivalent to axiom of choice. In other words, if we assume axiom of choice to be true, then we can write a proof for this result. Okay, which I'm not going to do today. Okay. Now, another thing. Okay, so there are advantages and disadvantages of Zorn's lemma. Okay, obviously. In other words, not disadvantages but limitations would be the better word to say. Okay. Because it assures you the existence of a maximal element. Okay. In other words, you want the existence of something big, this theorem will allow you to show that existence. But that existence is not constructive in nature actually. So in other words, okay, for example, sometimes we prove that something exists and we construct it actually. So we know that how you reach to that particular thing. But the trouble with the Zorn's lemma is that it just tells you that it exists, but there's no way to construct it actually. That's another limitation of it. Okay. Anyway, is there? Let's do it. Banach Theorem. So, are we happy with this? Okay. Zorn's lemma. So it says that if you have a poset, it's like a partially ordered set taken to the partial order, fluxual, symmetric, antisymmetric, not symmetric, and transitive. And if every chain has an upper bound, okay, in the given set, then the set has a maximal element in it actually. That's what the Zorn's lemma is.
So set is P.
Yes, maximal element. Okay. P has a maximum. So I've written it. With respect to this one. Okay. Okay, so let's get into the Hanhn theorem for defining the Hanhn theorem. I would like to define something which is called a sublinear functional. Okay. A sublinear functional is like a bit weaker notion than linear functionality. Okay. So sublinear functional. So consider P as a map from the vector space X into R actually. Okay, under C. So X is a vector space. Not necessarily having a notion of size. So let P be a map from a vector space to R. In other words, it's a functional. And such a map is called sublinear functional. Functional. If it has two properties, that it must be subadditive. In other words, this subadditive property, that is, that for all points x and y in x, okay, if you compute the sum of, p of the sum, it must be less than or equal to p of x plus p of y. Okay? This must be satisfied. And so that's called subadditivity property. And the second is what we call the positive homogeneity, which says that if you have p of some scalar times x, okay, then this must be same as alpha times p of x, okay, where alpha is a non-negative number. Okay, so alpha is non-negative. So give me an example of sublinear function. This is very
f of
obvious
x is
example.
equal to x square.
It's like a norm is the easiest example of a sublinear function, because if I define p of x to be norm of x, then it, obviously you have this, what do you call, triangle inequality, this positive homogeneity, and so on and so forth. It's fine actually that any map from x into r, so if I have a map from x into r plus, it's also a map from x into r, so it's fine. R plus is a subset of r. Nothing wrong
At the
with it.
same time, linear भी है.
Linear line क्या
भी है और sublinear भी.
No, where I said that it's linear, so I said that it's sublinear.
Non-linear पर.
And positive homogeneity.
linear.
So it's both actually.
Triangularity.
Okay, so norm could be the one of the example.
Yes.
So what does the harmonic theorem is telling us?
No, bounded to bounded to
It's a pretty simple statement. It's not complicated.
show
So-
no bounded show
So harmonic theorem is
okay.
harmonic theorem is telling us, it's like a harmonic theorem for vector spaces, telling us that imagine you have a real vector space, and you can have also complex as well. The calculations are going to be a bit different. It has to be a real vector space. I hope that. Okay. And P is a sublinear functional. Sublinear functional on X. Okay. It's a vector space and P is a sublinear functional. Okay. Then if F is a linear functional, not a sublinear functional. F now is a linear functional. Okay. Functional. Okay. Defined not on whole space X, defined on a subspace Z of X, okay, such that this has this interesting property that f of x is less than or equal to p of x for all x in what do you call it, Z. So in other words, this point-wise comparison is there. Okay. extension of this linear functional which is going to be defined on the whole space and satisfy this property. Okay. Then f has, this f has a linear extension
To all space.
linear extension f tilde from x into r such that f tilde of x is less than or equal to this p of x from x in x and alright. How can I say it pictorially? Think about it. That okay, I have that's my space x. Imagine that's R actually. Okay, and I have a sublinear functional. Okay, which is defined on whole of x. So I have a p defined from x into r. Okay, and I have an f which is defined not on whole x but it's defined on some part of z, so it's like some part of x. Okay, f. But this f and p has a relationship that at each point of z, okay, you know, if you compute f of x, it can't exceed p of x actually. Okay, it's like the value of p at that point. Okay, so if this is true, then I can find an extension of this f, what do you call f tilde, maybe something f tilde, which is defined on now not on this part z, and you know it's like it's whole x, and still this property is preserved actually. Okay. So the property is preserved. Seems a bit uninteresting kind of a statement. We're going to see some of the applications of this, and we're going to see that that's a pretty interesting statement actually. That if you have a linear functional, so in some senses you can call it an extension theorem actually, which allow you, okay, to take a particular kind of a linear functional which is defined on a subspace, and you can extend it to the whole space actually. Okay. So that's what the Hanhn theorem is. Let's go for the proof of it actually. The proof is, as I said, depends on Zorn's lemma. Okay. Depends on Zorn's lemma. Here's a proof. We're going to do it in steps actually. Okay, the first step is going to be that let E, okay, the step 1 is going to be that let E is the collection, okay, of all G's, okay, such that G extends F, okay, so it's like a G extends F, and G of x is less than or equal to G of x. Okay. Okay. Can you tell me what are the what is the precise meaning of G extending F? What does it mean actually?
F tilde.
Domain is increased for F.
If of x is equal to G, Z, but
I said, what is the meaning of it having an extension actually? So what does it mean that G and F agree
For both.
in
on Z?
but
Okay. But G is a map, okay, from
x
Z to
R.
X to.
X to R. Okay. So G is a map from X to R such that G and F agree on Z actually. Okay. I can say it precisely that the domain of F is contained in the domain of G is contained in
Other way around.
other way around.
Yes. Domain of X.
Yes, domain of F is contained in the something like that. Okay, so that's a pretty simple calculation. I want to make sure that you know what does written out. It seems that what does it mean? So what we have done
Existence of extension is always possible.
in this case, it is possible. Not necessarily.
It may be null set. It may be a null set for now. We just have written this set.
But we're gonna say that this is not a null set because
Existence.
at least
G is equal to F.
F is there.
Yes. Who could have?
No,
No,
that's not necessary. Because F is not defined on whole X actually. So we're gonna show it's non-empty. Don't worry. We're gonna construct something which is show something which is there always.
सर मतलब extensions more than one भी हो सकती है ना?
Yes, तभी तो set कर रहे हैं. तभी set कर रहे हैं. So what we are going to do next is that I'm going to define a partial order on this set. Okay, and I'll show that the conditions of Zorn's lemma are satisfied. Okay, so that E be the collection of all such this. Okay, so that all such this. So using Zorn's lemma, we will try to imply, okay, existence of a maximal element in an E, in other words, maximal extensions. Maximal element in E, and let's call that F tilde. So that would be our first step. The second step would be to show that this F tilde is defined on
X.
whole X. So this is going to be another thing. That, this maximal element cannot have a a domain less than X. Okay, something smaller than X. And the third thing would be that this F tilde works. In other words, this property is satisfied. Okay. The third thing would be to show that it satisfies this property.
Sir, if it is from E, वो तो guaranteed है.
Yes, it's there. And then okay. The second step. And the third step would be basically something that we use here, we're going to justify it here. Okay. We're going to justify it in the third step. So let's begin with the first step. Let's begin with the first step. Okay.
लेकिन लिखने में कर रहा हूँ मैं पूरे से.
schema है कि सही वेरीफाई रहती है कि कोड पहले
वो शो कर रहा है ना, वो शो कर रहा है.
Okay. Okay. Now, how can we know that he is non-empty?